In this lecture, we will discuss again confidence intervals for a population mean. Recall that the objective of a confidence interval is to estimate something about a population which you cannot measure directly, often because the population is too large. In this lecture, we will be estimating a population mean, mu, also known as an average, when the population standard deviation sigma is unknown. Here's the formula for a confidence interval that we discussed last lecture. Here we took the best estimate, known as x bar, or the sample average, and we added and subtracted the margin of error, which is composed of a z-score times sigma, the population standard deviation, divided by the square root of n, the sample size. Now we're talking about situations in which we don't know sigma, the population standard deviation. In this case, sigma is unknown. Here we still take our best estimate, x bar, the sample average, and we add and subtract a margin of error that is calculated slightly differently. Here we're going to take a number from the t-distribution, which we'll talk about in a moment, and we use the sample standard deviation. In other words, the statistical standard deviation calculated from the sample data. Your degrees of freedom, sometimes subscripted df, will always be equal to the sample size minus 1. That's n minus 1. Next, we'll discuss quickly how to use the t-tables to find these z and t numbers for our confidence intervals. This is a typical t-distribution chart. You'll notice along the top that there are various types of confidence intervals you can make. You can choose between an 80% interval, a 90% interval, a 95% interval, a 98% interval, and a 99% interval. If you want to get the z number for a confidence interval for the mean, where you know the population standard deviation, you go all the way down to the bottom row where you see that it says z in parentheses with an infinity. In this case, you'll notice the 1.96 can be found right here, which is in the column for the 95% interval. However, when we calculate confidence intervals, when the population standard deviation is unknown, when we don't know sigma, we have to use a degrees of freedom row. Remember that the degrees of freedom is equal to the sample size n minus 1. So if your sample size were 21, for example, your degrees of freedom would be 20, and you would get your 80% interval using the number 1.325 in the formula. You'd get a 90% interval using 1.725, and you get your 95% interval, your 98% interval, and your 99% interval by substituting these three numbers in for t. Let's do an example problem together to practice how to make a confidence interval when the population standard deviation is both known and unknown. Pay close attention to the bold words that makes the next two example problems different. 51 randomly selected Statistics 244 students at PSU were surveyed about their study habits. The sample's average time spent studying per week was 14 hours, and the population standard deviation of study time among college students is known to be 5 hours. Find a 95% confidence interval for the population mean study time mu, which would be the overall average study time of all PSU students. In this case, notice the bold words tell us that we do know the population standard deviation. It's 5. So we can use the confidence interval with the z. The important information from the question is that the sample mean was 14 hours per week. Here we see that there. The z-score of 1.96 comes from the fact that we know that the population standard deviation, sigma, is 5 hours. Here we indicate sigma equals 5. 1.96 also guarantees us a 95% confidence interval. Our sample size here is n, 51. That's because 51 students were randomly selected, and those 51 students were recorded for their average study times. Using this information, we're going to take our sample mean, we're going to add and subtract 1.96, multiplied by the standard deviation of 5 divided by the square root of the sample size. If you add and subtract 1.96 times 5 divided by the square root of 51 from 14, you'll get the following interval. Here we get 14 plus or minus, and if you calculate the margin of error, we get 1.37 to the nearest hundredth. You can also write that confidence interval like this: 12.63, which would be 14 minus 1.37, all the way up to 15.37, which is 14 plus 1.37. Here we would claim that with 95% confidence, the interval that we have just calculated, including all numbers between 12.63 and 15.37, includes the true population mean. Yes, there's a 5% chance that our random data led us to a faulty interval that does not include the true population mean, but we have to be okay with this 5% chance of error. Observe the next example question, which is very similar. However, I've changed some key words. 51 randomly selected Statistics 244 students at PSU were surveyed about their study habits. The sample's average time spent studying per week was 14 hours, with a sample standard deviation of 5 hours. Note here that we do not know the true population standard deviation because it was not given to us. Find a 90%, 95%, and 99% confidence interval for the population mean study time mu, the overall average study time of PSU students. First, we'll calculate the 90% confidence interval. Here we will take the 14 average that we saw in the sample, plus and minus 1.676. This is the t number that comes from the t-charts that I showed earlier. You'd have to go to the 50 row for 50 degrees of freedom, and you'd have to go to the 90% column for a 90% confidence interval. We still have to multiply that by the sample standard deviation divided by the square root of the sample size. That is equivalent to taking 14 and then adding and subtracting 1.17, which gives us a confidence interval of 12.83 up to 15.17. For the 95% confidence interval, we have 14 plus or minus 2.009 times 5 divided by the square root of 51. You'll notice that the only thing that changes from a 90% confidence interval to a 95% confidence interval is that t number in the formula. That t number guarantees us, in this case, 95% probability, and in the past case, 90% probability. This is equivalent to 14 plus or minus 1.41, or an interval of 12.59 to 15.41. Again, here we would say with 95% confidence, this interval includes the true mean study time per week of a Portland State student. Finally, we calculate the 99% confidence interval, which is 14 plus or minus. I've gathered all of my t numbers over here, and I know that for a 99% interval with 50 degrees of freedom, my t number is 2.678. I multiply that by my standard deviation of the sample over the square root of my sample size. I get 14 plus or minus 1.87, and I calculate my confidence interval to then be 12.13 up to 15.87. Again, for that interval, I would say with 99% confidence, it's the interval of numbers between these two values that contains my true population mean somewhere inside. Again, in this case, there's a 1% chance error. In other words, the opposite of 99% would be a 1% chance error that I have missed the population mean with my interval. Again, that's not a very high probability, though. Another thing you'll notice, and this is part of the lesson today, is that the confidence intervals get narrower as you have a lower percent confidence, and they get wider as you have a higher percent confidence. This is a compromise that we have to make with confidence intervals. If you want to be more confident, you're going to sacrifice some precision. In other words, to be 99% confident, your interval is going to be wider and potentially less useful. That is partly why most fields that utilize statistics have compromised on a 95% confidence interval, splitting the difference between being very confident and yet still having an interval that's a little bit narrower and more specific. Let's do another example, and we'll use the calculator for this one so that we can remind ourselves how to use the calculator for confidence intervals, as well as how to change the calculator confidence interval to account for the standard deviation being unknown. Here, the national average for the number of students per teacher for all U.S. public schools is 15.9. A random sample of 12 school districts in Oregon and Washington showed that the mean number of students per teacher was 19.2, with a sample variance of 4.41. Estimate the true mean number of students mu per teacher in the entire population of school districts in Oregon and Washington using a 99% confidence interval. Again, we were apparently unable to sample every single school district in Oregon and Washington, which would represent an entire population. Instead, we took a random sample of school districts in Oregon and Washington in an attempt to make the estimation of what the true mean really is. Here, I indicate that a sample of 12 school districts, produced a sample mean of 19.2 students per teacher. That's where you see my X bar is 19.2. Because we took a sample of 12 school districts, my sample size is 12, and I know that my degrees of freedom will be 11. In this case, I can go to my t-chart and find the t constant number, which will be 3.106. Again, in this case, I want a 99% confidence interval, so I have to go to the 99% column of my t-chart, and then I have to go down to the 11th row for 11 degrees of freedom. Here I gave you a sample variance in this question, not to confuse you, but to remind you of the relationship between a standard deviation and a variance. A sample variance is denoted S squared, and in this case, it's 4.41. A sample standard deviation is the square root of the variance. So if you take the square root of 4.41 on your calculator, you will get 2.1, which is the number we want to use in our interval. Here we're going to use our TI-84 calculators to calculate the confidence interval. We go to our Stat button, scroll over to Tests, and this time we're going to leapfrog the z-interval and use the t-interval option. T-interval because we're using a t-distribution as part of our confidence interval. Here we enter the necessary information to formulate the confidence interval, which we got from our problem. The sample mean is 19.2. We recalculated the sample standard deviation to be 2.1 from a variance of 4.41. Our sample size in this case is 12, and our confidence level is 0.99, indicating that we'd like to be 99% confident. Now I calculate. You see that the interval ranges from 17.317 to 21.083. I can indicate that here, if this were a test, for instance, using my interval notation. If you'd like to use your calculator on a test in this class, simply make sure you indicate what values you input and what option you used on your calculator. Here, again, if this were a test in my class, I could put the 4 pieces of information that I got, and then I could show you that I put this into a t-interval option on my TI-84 calculator. Then I can show you the confidence interval, and that will be enough on a test to show me that you know how to find a confidence interval. There is a follow-up question that I might ask in this case. The follow-up question may be something like, do Oregon and Washington school districts have more students per teacher, which would be a bad ratio, than the national average? Recall that the national average in this case was nearly 16 students per teacher, and that our interval of confidence for Oregon and Washington schools is ranged between about 17.3 and 21.1. In other words, we have a lot of confidence that there are more students per teacher in Oregon and Washington than there are as a national average. This is a bad thing for Oregon and Washington if these statistics are true.